This is Hacker Public Radio episode 3469 for Thursday the 18th of November 2021. Today's show is entitled Linux Inlaws S01E43, The Great Battle or Not, and is part of the series Linux Inlaws. It is hosted by Monochrome and is about 69 minutes long and carries an explicit flag. The summary is The Great Battle nor Not.
This is Linux Inlaws, a podcast on topics around free and open source software, any associated contraband, communism, the revolution in general, and whatever fancies your tickle. Please note that this and other episodes may contain strong language, offensive humor, and other certainly not politically correct language. You have been warned. Our parents insisted on this disclaimer. Happy Mom? Thus, the content is not suitable for consumption in the workplace, especially when played back in an open plan office or similar environments. Any minors under the age of 35 or any pets including fluffy little killer bunnies, your trusty guide dog, unless on speed, and cute T-Rexes or other associated dinosaurs. Welcome to Linux Inlaws Season 1 Episode 43. The Great Battle or Not. Martin, how are things?
Oh, very much looking forward to tonight.
Excellent.
We have our dear friend from Redis Days with us.
Speaking of
have
which, yes.
Interesting discussion around.
Indeed. But before we go into the battle mode,
okay.
Yes, maybe David should introduce himself. David, over to you.
Yeah, I mean, I'm an old friend, right? Me and Thomas we're already kind of part of this podcast as guests.
One of the grumpy old corners, exactly.
Exactly. And introducing myself, I guess the reason why Christoph asked me to join this is because I worked for some database companies in the past, for instance, Ingress as a relational database system vendor, then for a small graph database startup, then for Couchbase as a document database vendor, and now I'm working quite a lot with Redis Labs as the vendor of let's say a real-time data platform, whatever. And I'm also having a little consultancy company in Germany, which is called NoSQL Geeks, right?
And full disclosure, Redis Labs is the place where we all met initially before Martin defected to something called. Martin, you could.
Oh, sorry. Yes. Bright lights. Yes.
Yes. Sorry. Okay, indeed. Richard, if you're listening, the address is sponsor@linuxinlaws.eu. Okay, guys, the idea behind tonight is actually to shed a little bit of light on the history of both camps in terms of where SQL is coming from, where NoSQL is coming from. Full disclosure, Martin, before joining Redis Labs, was kind of old school and worked for a company called Enterprise DB. But maybe, Martin, you want to shed some light on this stint in your life too?
Well, it's more than it is
never mind
definitely
the Oracle period. Yes,
a stint. Yeah, but yes, I have been working with databases ever since I started working. In fact, after uni, that is. So mainly, well, as you mentioned, Oracle, and then in later years, Postgres and associated fringe.
So why did you actually then consider a NoSQL database employer?
Well, there are obviously advantages to lots of different technologies, right? So, and I think not foregoing any conclusions. I think the conclusion,
and of course, money
be that there is a database for everything.
And money didn't have anything to do with it, of course.
No, we don't get paid for these.
Of course not. Okay, guys. Now after the intro round, maybe each and every one of you could could give a little bit of an historic breakdown of actually where the particular technology came from. Let's start with you, Martin. Where does the SQL come from? Feel free to go back to mainframe times if you have to.
Okay, so SQL is actually a language, as in structured query language. So if you talk about SQL versus NoSQL, I mean, there is also there's two different definitions of NoSQL, which probably David will pick up on. But where do these things come from? Well, there was for those of you who've studied computer science, you're probably familiar with Michael Stonebreaker. He did many things. One of his
Ingress, for instance. Right?
Indeed, yes. One of his main.
One step at a time, gentlemen. The guns haven't been drawn yet, so rest assured.
Yeah, so that whole kind of Ingress was the origin of many different relational databases at the time, Oracle being one of them, and so on. So it all comes from that same background. And yeah, I mean, relational databases have obviously progressed over the years. They are not just only relational data stores anymore. But again, we'll come to that later. And they are probably the majority of all, let's say, transactional systems in the world run on a relational database, I would say.
Interesting. Over to you, David.
Yeah. I mean, what is the question? What is the NoSQL or where the NoSQL movement is coming from? I'm not sure. I'm not sure if I can puzzle this together, but let's say it this way, right? So originally there were traditionally already more than relational database systems in the past, right? So I think even in the late 80s we had hierarchical database systems and stuff like that, right? And then I would say late 90s maybe, right? Or maybe I'm wrong. Maybe even earlier, object databases arose. So it was not a new idea.
Definitely earlier,
yeah. I think earlier, right? It was not a new idea to actually, let's say, have alternative models, right? And even if relational databases are based on the relational algebra, which kind of makes sense and so on, there's always this kind of strange thing that you need to kind of track the view on your data or by using tables and columns and rows and whatever, right? So meaning at some point, or I would say maybe 2008, around that, right? There was the NoSQL movement happening where the basic idea was to say, hey, instead of using a database system which aims to be a general purpose database system, which is more or less the case for a relational database system, at least they are promising it. We will maybe see during this discussion here that this promise is not entirely fulfilled always. Let's have database systems that are more multi-purpose systems, let's say, right? And such multi-purpose systems are, as the name is indicating, are good for specific purposes, but maybe not for other purposes in the first step, right? And with this kind of intention, we would basically have also different methods of accessing them. So, for instance, CouchDB is something I worked with in the past a bit. In the context of Couchbase, it's not the same, by the way, right? But CouchDB is a document database system where you kind of index your data by defining our views, let's say, right? Those views are accessed via REST API, and they are kind of implemented by using MapReduce, let's say, right? So I would say this is quite a different way of accessing data versus having the structured query language, let's say, right? And there are other systems as well that are falling into this category, like key value stores. For instance, Redis, which is much more than a key value store. We can talk about this later. But again, the idea was, have specific data stores that are fulfilling specific purposes. But better than the relational database system, whatever better means in this context, right? For those purposes, if this makes sense.
Just to summarize, structured query language as an SQL implies that you have a predefined structure consisting of tables, and these tables are subdivided into rows and columns so a usual table, whereas a NoSQL doesn't have this constraint. Is
Doesn't
that
need to
fair?
have the NoSQL. This is actually funny, right? Because initially, historically, as far as I remember, when I got in touch with NoSQL the first time, it actually really meant that we are doing something not relational, let's say, so non-relational, right? So the no was basically saying there is no SQL, but nowadays this is different, right? So the no was kind of reinterpreted in between, which means it is now not only SQL, which means a NoSQL system or can actually have a query language, and it can actually be even a query language which reminds very much about the structured query language, right? So your summary was not entirely true in this context, let's say, but yeah.
Where do you see these two ecosystems today in the light of shenanigans like Internet of Things, like hipster languages, implementing microservices and application monoliths being rapidly deconstructed? So you have your ecosystem of applications all having different having different persistence requirements and also different expectations of the persistence layer, which essentially a database is. Martin, maybe you want to go first?
Yeah, I think there was a couple of questions there, right?
Back yourself out, Martin, by all means.
But if we touch upon, I guess your question comes down to, for which applications would you choose which technology? In short, so
modern applications. And I'm not talking about
modern applications.
Yeah, sorry.
What's a modern application?
Like anything not being in general ledger that has been running on a mainframe for the last 30 years.
Not written in Java, or
not being implemented in COBOL, right?
Okay. I was going to go for Java myself.
Never mind Fortran or Java. Yes.
Yeah. No, I mean, but the things like microservices, they're just a concept. So which data store you choose, but you have a point about the persistence, right? If data is temporary, then you may choose to go with memory storage only, which again doesn't make any difference to the underlying database technology, whether it's a Postgres or Redis. You can decide not to use persistence with either, right? So then it becomes temporary data because it's in memory, it's not persisted, not durable, whatever you want to call it. So I don't think there is there are obviously typical use cases for a database, right? Which is like with a call it a relational database, but they are typically used for transactional systems because of the durability requirement, because people don't like to lose their transactions. They like to have them in as many places as possible, and ideally on something that is not volatile storage.
Depends on the use case, right? I mean,
yeah, exactly.
Depends on, or if it is session management, you might just live with
the
fact
that's what I meant by temporary data, right?
Yeah, that your data is gone or whatever. And there's also, or let's say,
however, you can also just use Postgres in memory mode only, for example. So then you're not really.
I'm not a Postgres expert, but I would.
It's not really related to saying, "Oh, I have to have a key value store. I have to have NoSQL to store something in memory," right? It doesn't matter which.
But it's all about efficient access, right? So, meaning, let's assume you have a memory database system, which is a relational database system, right? And let's assume that you stick with the relational paradigm by not being able to bypass it, right? Because you're using a relational database system. So what you need to do is, if someone is querying the data, even if your data is in memory, right? You need to kind of parse this query, right? You need to maybe or build a query execution plan, right? Or by doing some enumeration steps behind the scenes, right? Or maybe you involve some statistics about the data in order to find the best plan, blah blah, right? And then
just a quick question for the two listeners who are not database experts. What's the query execution plan? before we get too technical.
So basically, there are multiple steps if you execute a query, right? So you give the query, which is basically the query string, and this query string is in the first step parsed, let's say, right? And then based on the parsed SQL, you transfer it in something more low level, and then you say, okay, fine, within my steps which I need to do, right? There is maybe some selection, there's some projection, there are some index scans, or in order to retrieve some data, there are maybe some low-level operations like merge joins or whatever, right? And in order to efficiently fetch the data you're interested in, you need to plan how to do this, right? And the plan how to do that is the query execution plan.
Ah, okay.
And this is something you build up front as part of the query execution. And if you have SQL, you get usually, even if it is a memory, all this overhead of doing that, right? And then at some point, as soon as you have the query execution plan, you would basically say, okay, fine, I'm now executing the query by scanning maybe some indexes that are in memory or whatever, right? And then finally you fetch the data. Here in this case, Martin mentioned, okay, if it is a memory, it's a memory, then it's fast, but it's not entirely true. The question is how complex, how big is the time complexity in order to be able to fetch the data from memory. And with the relational model, there's much more overhead involved than with a key value store, because in a key value store, you don't have a query you need to parse, or you don't need to build a query execution plan. The only thing you need to do is you need to have an O of one. You have an O of one operation, which is basically fetching the data from a kind of giant hash map within memory, let's say, right?
Well, a C program. Yeah. Okay.
You see,
yeah, but I mean that's the point, right? It's simple. And the other thing is,
however, I was just wanting to pick up on your parsing plan, because clearly, if you use a key value store, you also execute a certain command, whether that's a get or a put or whatever it is, right? It still has to be parsed.
Yeah, but it's not like a SQL query, man.
No, but this is it. You are only retrieving one value, so in a SQL query, that would be one operation as well.
Yeah, but Martin,
there's no joins involved. There's no merge joins. There's no.
But if you would use your SQL, so let's assume you're right. If you use your relational database exactly like a key value store, right? Uh-huh. So if you have a relational database system and you do something like select star from my table where this column equals exactly that value, right? Yeah. Then there is anyway more overhead than just doing a get key, let's say, right?
Yeah, but select star isn't a get key,
if you're
right?
in the where clause,
not the same. It's not the same operation.
Guys,
no,
one speaker at a time, if possible. Thank you.
Well, I'm basically disagreeing with it.
Nah, but okay.
I guess it's a single operation, right?
Maybe
it's a single key operation, so therefore a select star is a multi-row operation.
Maybe I can call order right now.
But the thing is the following. Okay, let me kind of explain it step by step. Okay, the thing is the following.
As long as you stick to the facts.
If you have a pure key value store, right? Everything is an item, is a key value pair, which means the only way how you can access the data in a pure key value store is basically to fetch the entire data you're interested in by knowing the key already, right? Mm-hmm. So which means that your object, or let it be an object maybe, or something which was basically serialized and then stored in the key value store, is something like completely there as you need it, right? And the underlying data model, let's say, right, is so simple that you just need to do a get key and you get your value back, whatever this is, let's say, right? So now in the equivalent in a relational database system would be, okay, hey, or maybe your type is reflected by a table, let's say, right? And maybe you would like to have all the data which is associated to this. Maybe there's a user table and you would like to have all the user data the same way as you would maybe fetch the entire user object if you basically do this get user demire, whatever, right? Mm-hmm. Now, in relational database systems, just an example, you would do something like select star from users, right? Where my user ID equals demire, right? So now processing this query is much more expensive than just doing this get, right? On the hash map. Processing this query basically means that you need to parse it. There is anyway a query execution plan, because it's a general purpose system, right? So you go through the entire stack, let's say, and finally you fetch the data and give it back to the client, but it's more complicated. And In this example, you would do a select star in order to fetch the entire user details, the same way as you would fetch the entire user by fetching this serialized object, which is in your key value store. Now, the thing is as well, right? If you use a relational database system, then relational database systems usually come again with entire stacks of processing data, right? There are multiple components that are involved. There are transaction managers, for instance, right, that are detecting deadlocks of transactions. They are doing maybe locking. They are maybe doing lock escalations or blah blah, right? Or there are index scans and so on. The whole thing of executing a query. So. In a key value store, the model is such simple that you basically just fetch it by a specific key, right? That all of this stuff doesn't play a role in this context, right? The stack is basically not as deep as with the relational database system, I would say, right? And this needs to be anticipated. So it makes a difference if you store your data in memory in a relational database system versus a key value store in this sense. And the other sense is, let's say the last two sentences regarding this before you talk, is basically the underlying data model has an impact on, let's say, the scalability of your system, right? Indeed, if you use a key value store, pure key value store, we are only interested in fetching data by its primary key, right? Mm-hmm. But this kind of limitation in the first step is also giving us a benefit of being able to scale this stuff, right? Because what we can easily do is we can easily apply something like a hash function on this primary key, distribute the data based on this hash function across many nodes, right? By being able to scale reads and writes. Now, with the relational database system, even if it is on memory, you can't do this that easily. Indeed, you can partition data, right, or in specific ways and so on by basically defining logical partitions, but it's much more complex. And again, if you would like to keep the guarantees of your relational database systems, like ACID compliance and so on, right, which is something you compromise with key value stores in this sense, there's again additional overhead involved for something that simple, like fetching a specific key or changing a specific key. So it makes a difference. It's not just the in-memory aspect, right? It's about the entire characteristics of the system and not just about it's in memory. So it doesn't matter if it's this system, which is memory, or that system, which is memory.
And before we go even further, maybe Martin could explain, because he's old school, what is ACID compliance exactly? Before we lose our last listener or something.
Yeah. First, I'd like to kind of agree with David, because the thing about the memory piece was really about, because Chris mentioned the persistence piece, really, and you make a valid point that key value stores are simpler and relational databases are generally more complex, more feature rich, and both they come with trade-offs, which is fair. So if we then go on to the ACID piece, they're really a set of properties for database transactions or databases that give it certain guarantees, right? We talk about, say, isolation, right? Isolation. If you have multiple users using the same database, they don't want to be able to see the others' in-flight transactions, things like that. There is obviously durability guarantee, which is what the D stands for. So if someone does a database transaction, then it's guaranteed to be durable, meaning that if you have a power outage, then it is possible to retrieve this data. And the other two are atomicity and consistency, which again are really associated with relational databases. You can only go with consistency. It's really a state transition that is always the same, right? So if we're going from one state to the other, then that consistency is the guarantee that it has happened as a single unit, that there aren't any separate steps in between that can be interrupted, right? So if someone writes, specifically with writes, this is relevant, right? If we're saying I'm going to deduct £100 from your credit card balance, then we want to know that happened in one step rather than in two steps where it could have failed halfway through, and you end up with...
this is actually atomicity, right? Just saying. what you just described is basically atomicity, right? So
yeah, sorry, I moved on a little bit, but so these are the main characteristics that, yeah, I mean, with a key value store, you can have durability as well, which we know from Redis. I can't remember what Couchbase's or CouchDB's model was.
Yeah, but Couchbase actually was originally more disk-based, right? So it's not exactly the same as Redis, where everything needs to be in RAM. But Couchbase, or the initial one, I think they introduced in between another feature, which was diskless bucket or whatever, right? But initially, it was quite typical to evict data down to disk, right? So persistence was actually kind of baked in, right?
But going back to the absolutely controversial issue of an execution plan, I might interject that actually not every NoSQL database is a key value store. Because you have graph databases, you have time series database, and all the rest of them, right? So
indeed. But this was not the point, right? We didn't talk about, hey, this is only NoSQL or not NoSQL, but the point, our controversial discussion was about, it doesn't matter which in-memory data store you're using. If it is in memory, it's always as fast as any other in-memory database system. At least this was what I interpreted from Martin's statement, and this is a wrong statement.
No, that was
please.
No, it's because Chris.
But this doesn't mean that there aren't other kinds of database systems,
yes.
NoSQL database systems out there, right? But their own specific characteristics beyond our key value stores. Maybe one last thing about our consistency, right? So consistency in relation database systems does not just refer to, let's say, physical consistency or state consistency or whatever, right? It especially also is logical consistency. Exactly. So what you do is you start from a consistent state, or your transaction starts from a consistent state, right? And it ends in a consistent state, whereby what this consistent state is actually kind of well defined by having constraints. So for instance, referential integrity or not null or whatever, right? As constraints. Yeah.
Mm-hmm.
Interesting perspectives, gentlemen. But given the fact that now with the latest edition of mobile crazes and other interesting, fascinating use cases, databases actually have to scale planet-wide. Just wondering, how do both camps scale up to that challenge?
Do you want to go first, David? Shall I go first?
Well,
go ahead.
Why don't you go first?
I think what we've seen in the whole database landscape is that people keep adding to it. And when you specifically talk about planet-scale databases, then the likes of Google and Microsoft have built their own tech, right? And yes, you can argue that other databases may be able to fulfill that role as well. Some better than others, clearly. Partly due to heritage, partly due to their premise of what they are trying to achieve. But if you're talking about planet scale, then there's a number of factors involved, right? There's latency, there's consistency, there's partitioning, or the cap theorem. Isn't that right, David?
Yeah, indeed.
Very much so. But before we go any further, what exactly does the cap theory mean for the people who do not know? I think he's Professor Brewer these days, right? Maybe I'm wrong. At least doctor anyway.
Maybe. So should I take this?
Please, David, go ahead.
So let's assume that, so C is consistency, A is availability, and P is partition tolerance, right? Or let's assume that the P is kind of a given, right? So if you have a network partitioning event, then the system is basically tolerating this by not falling into pieces, let's say, right? So meaning, usually we're talking about AP systems versus CP systems, so available and partition tolerant, and consistent and partition tolerant, right? So now it's actually quite interesting that the the CAP theorem is often a little bit misinterpreted, right? Or so at least I have seen this with customers a lot, right? And I hope that I'm not misinterpreting it now, but I'm pretty confident that this is not the case. If I am, then you or the listeners might correct me. But so let's say the availability is actually not just the availability in the context of if nodes are up or down or whatever, or if the system is highly available. This is kind of overlaying with this, but at the end, availability means the availability to perform requests, right? A system which would basically always return an error is not available, even if all the nodes are up and running, right? So availability is the availability to be able to execute commands at the end, right? Consistency, it's kind of...
So sorry to interrupt. Yeah. On that subject, then, I'm just sort of clarifying for the listeners. Are we saying that if a system is up, then it's available, no matter whether it can return?
No. What I'm saying is, if a system is up and running, but the system would return you an error message for your request, it's not available to execute the commands, right? Which means it's not available if it returns error messages only, right? Even if the nodes are up and running. Let's say this is the statement. Okay, so let's clarify that this is the availability we mean, right? The availability to execute commands, actually, to respond to requests, right? This is the availability we mean here. The consistency refers to, let's say, state consistency, or let's say the observed state by clients. And what helps me at least is to imagine a distributed system in a sense as a black box in the first step, right? So kind of don't be interested in the first step how it is looking inside, right? Let's just look at it as a black box, right? And then there are multiple clients connected to this black box, and inside one client might be connected to node 1, another one to node 3, whatever, doesn't matter, right? So let's say multiple clients are connected to this black box. Now, what's important is that if multiple clients would request a specific data item at exactly the same point of time, right? A system would be consistently behaving, right? If all the clients are getting exactly the same result, right? Whereby in an AP system, it would be tolerated that some of the clients get another result than other clients, right? So now, why is the CAP theorem easy to prove, in a sense, right? Let's imagine you have just two nodes in your stateful distributed system, right? And so let's say node 1 and node 2. And let's assume that you have a single client here in this example, right? And the single client is performing a single write operation to node number 1, right? In addition, node number 1 is aiming to replicate the data to node number 2. Right. So now, again, setup is client writes to node number 1 replicates to node number 2 under normal circumstances. Now, what we need to have now in order to make sense out of this, it is a network partitioning event, right? Let's say someone cuts the wire between node 1 and node number 2, right? So the client is performing the write operation to node number 1, right? Node number 1 is now basically not able to reach node number 2, right? Because node number 1 is not able to reach number 2, but it aims consistency, and aiming consistency basically means that are you still there?
Yeah.
So aiming consistency basically means that the state on node number 1 and the state on node number 2 should be the same, right? So meaning, but here under this network partitioning event, node number 1 is not able to reach node number 2, which means that node number 1, if it aims consistency under the circumstance of this network partitioning event, right, would need to communicate an error to the client, right? It would need to tell the client, hey, I can't unfortunately reach the desired consistency level, right? So error, right? So meaning, if it is a CP system under the circumstance of this network partitioning, it would basically be not available, right? So this is because why you can only have either an AP or a CP system. Let's assume the system is more available than consistent, right? Or behaves available instead of consistent, then it would actually not care about the fact that it can't replicate the data over to node number 2. It would basically just accept the write operation by acknowledging the write as successful to the client, and would eventually sort the replication out later, right? In this case, the node number one or the system behaves are available, right? Because it responds to the request, but it's not consistent, right? Because it can't guarantee consistency without ensuring that the data is basically the same on all the nodes, let's say, right?
Mm-hmm.
Hope this makes sense. Yeah? Well, hopefully not a too screwed up explanation of the cat theory.
It does to me.
Just,
Martin, what about you? Excellent.
Yeah, that's all good. Not sure if we answered your question.
What was the question? The question was about what is the cap theory?
I think that was a pretty good description of the cap theory.
No,
yes.
there was a question before that. Yeah.
Yes,
Sorry.
indeed.
What was the question before that?
I'm blanking.
No, you were talking about planet scale databases.
Yes, indeed. Scalable planet-wide databases. It's been a long day on the database road.
I think Martin said something very interesting and useful there, which was basically that latency is playing a role across geos and so on, right? And the thing is that especially if you have a high network latency between two regions, let's say, right, because of physics, just because of physics, at least before quantum computing is maybe in vogue. I'm not sure if this solves it, but sounds like it.
That will be next week, right?
Yeah, maybe. Then it takes a while to transfer a state from A to B, right? And let's say if you have a planet scale database and you aim for consistency, then as just explained, you would typically need to have synchronous replication from one side to the other, right? And this synchronous replication would basically have an impact on your performance, your workload, right? Because then your client would basically need the let's say source side or target side, if it is active, it's bidirectional, but you will basically need to replicate it over before you acknowledge the client, right? And given that the performance from the client's point of view would be impacted, which is the reason why most planet scale database systems, I would say, that want to operate at scale, but might be a question of requirements, are voting more for availability over consistency by doing asynchronous replication across geos, let's say, right?
Just for our dear listenership, active, of course, meaning that if you have distributed clusters across the planet, each and every application accessing their own cluster instance can write to said cluster instance independent of the other ones.
Exactly. You can write and read from each side.
Exactly.
Active. Yeah. Whereby in active passive, you can only write to, let's say, the source side, but optionally maybe read from the target side, right?
So, given the latest craze about Netflix streaming services and all the rest of it, which clearly demand a kind of planet-wide scalability, and probably a streaming service is not the best example, but you get my drift. What do you think? Which approach would scale better? The old SQL stuff that has been around for the last 50 years? Or this newfangled NoSQL thingy used by the hipsters with the long beards and Rust and Python programming language or whatever?
Yeah, as mentioned before, right? So we are voting, or in this case, for scalability over scalability and availability over consistency. Often, right? Doesn't need to be the case. There are also NoSQL systems that are behaving consistently. Again, they are multi-purpose systems. It's not really the case that you can say that NoSQL system or whatever, right? What you can say is there are different flavors for different purposes, and at least for something like document database systems at planet scale, let's say, or key value stores at planet scale or level, as mentioned by you, right? I would say it's most common to do our asynchronous replication across sites, which means that we kind of favor availability and scalability over consistency, and relational database systems traditionally are, vote more for consistency in this context, right? Because they want to be ACID compliant.
So, Martin, does this mean that SQL has had its day, as in it's dead?
Not really. I think, as David, or you described the use case, is the Netflix use case, for example, is if you are connected to your local Netflix instance, wherever that may be in Europe or the US. You don't really care if your US instance also has the same data, unless the Europe instance goes down and you get redirected to that. So this is a slightly different scenario from a, there's always the financial application, right, where consistency is more important. So there are, you can solve the first problem with lots of different technologies, depending on which consistency model you choose to use and which replication model. It's not. Yes, there are more. I think what you're kind of aiming at or trying to get to is that the scalability of a NoSQL, not a NoSQL. Yeah, let's call it NoSQL, is easier because of the way the data can be partitioned.
Some flavors.
But maybe. Yeah. Martin, do you really think that after the imminent zombie apocalypse, credit card transactions will matter anymore?
What matters then?
Netflix, asking, of course.
Right? Netflix, Netflix. And how do you pay Netflix?
Yourself.
How do you pay for Netflix then?
Just asking. That's the point.
Okay. Okay, good.
You heard it here first. Netflix will keep running after the zombie apocalypse.
Maybe. We did have a little fight here, right? Initially, and maybe for no reason.
A technical discussion comes to mind, David. Sorry.
It was anyway fun, but let's maybe state that it is not a direct competition anymore anyway, right? Because what was already mentioned by Christoph at the very beginning is our microservices. And if you talk about microservices and having your application as a distributed system by itself, right, you anyway need to kind of take some trade-offs into account regarding scalability versus consistency and so on, right? Or availability are taken into account as well for your entire system, right? And the data store is one puzzle piece there, an important one, right? And a common pattern in microservices is to say, okay, each service uses, or each microservice uses its own data store, right? And the second idea is if each service uses its own data store, right, then it should use the data store which is the best fit for the service, right? Mm-hmm. And sometimes the best fit is a relational database system. And maybe this is true for something like financial transactions, because relational database systems are good in that, right? So they have something like money data types, or for instance, or by not dealing with something like floating point numbers with specific precisions, but exact values. They have asset compliant transactions or completely are serializable and so on, right? So meaning for something like a money transaction to use a relational database system, maybe not the worst idea, right? So, but in your distributed system, which is, let's say, having a bunch of services in order to offer you the application, there are other services with different kinds of requirements, right? Another service might have much higher scalability requirements, right? And what is the benefit of having a service which can scale tremendously, right? But the data store can't scale together with it, right? Because it becomes a bottleneck because it needs to sit on a single machine, or there is across a few machines or a lot of overhead to do the transaction management and so on, right? So you get into trouble regarding the scalability criteria, which is in this case maybe more than just a non-functional requirement. So what you need to do is you need to use the data store which makes most sense for that. And for instance, if you manage sessions, you would end up with a key value store. Maybe if you have a product catalog, you would maybe end up with something like a document database system. If you do network analysis, right, so finding optimal flows or shortest paths or dealing with social networks or whatever, maybe a graph database is the best choice, right? Because it allows you efficient traverses without scanning indexes. Right, which is not guaranteed by relational database systems, right? So meaning, the idea is choose the right data store for the right kind of service based on your requirements. And in this context, it's not actually a competition, right? They are living kind of as creatures together in the same kind of microservice architecture, right?
Reminds me of the land-based dinosaurs and the thing kind of we're now looking at called birds. One of them survived, one didn't. No, I'm joking. Martin, anything you want to plug in the NoSQL world?
By the way, are we talking about NewSQL as well, or just NoSQL and relational? Right? Just asking because there is this archaeopteryx, let's say, right?
David, anything goes. Just go for it.
Yeah, I mean, I entirely agree. It's there are better fits for certain technologies. Certain technologies come with better functionality, like graph databases David mentioned, for example. Document databases, fine. Again, these are application type databases. We haven't even discussed the OLAP databases at all so far.
Martin, you just go for it.
No. So I think what we've concluded so far is that in general, NoSQL databases are better scalable. They are, in case of key value store, lower latency because of the reduced amount of transactions they need to do, whereas your relational databases are more multi-purpose and have therefore some overhead in various places. And some benefits in terms of ACID, etc. If we talk about so these are all let's call it transactional databases, right? Where you're talking about applications, Netflix's, PlanetScale, blah blah. People also use databases for analytical processes and reporting and all sorts of fun stuff like that. In that case, I would say the majority of all the tools out there are still very much SQL based. Yeah, call it relational. Your BI tools, etc.
To cut a long story short, as long as their mainframe is around, SQL has a place. Is that what I'm hearing?
Nobody uses a mainframe apart from Chris.
No, and a few
mainframes are clearly transactional, really. Right? This is so you could argue that they're in the okay. But if we talk about mainframes, they're monolithic in build, right? They're one single great big computer where scalability doesn't work apart from making it bigger. From that point of view, they're in the same camp as your most of the relational database.
Martin has a point regarding the analytical stuff, right? If you look at the analytical tools right now, and they are also more traditional, let's say, right? There is a transitioning happening from, let's say, something like or it's not actually any more true, right? It did swing a bit back, but anyway. So if you think about analytical stuff, right, the tools you're using in order to access this, or in the past or early 2000s or whatever, they were called business intelligence tools. They were reporting tools, and everything there was talking SQL, right? Because SQL is perfect for doing some expressive queries on your data, right? Group by aggregations, blah, blah, right? And there was actually even, or still is, a trend to do the same on, let's say, more modern analytical systems. But this is also not fair, right? Because it's a kind of coexistence. But let's say, let's take something like Hadoop, for instance, right? Hadoop initially was, okay, fine, we need to do some long-running analytics, and we just killed the problem with iron by having tons of compute nodes, right? Distributing the workload by using a pattern called MapReduce, right? So mapping, basically filtering, extracting, or mapping data to other data, and then basically reduce, applying the aggregation in the next step, and then maybe re-reduce across the nodes and so on, right? So meaning this kind of was a pattern used for a while to do analytics, right? Which was beyond SQL. But as far as I remember, the trend was actually like, now we have Hadoop, we materialize our analytical results back into the Hadoop distributed file system, right? Or we store it somewhere else. But in order to have expressive queries on that data, it would be cool to have something similar to SQL, right? And then there were basically frameworks rising that translated SQL queries into Hadoop.
It
jobs,
was just the storage layer.
Hadoop distributed file system is the storage. Hadoop itself was basically also the compute layer, let's say, right? But was then
some
abstracted.
solutions bypassed the whole compute layer. They just went straight to
or even that, right? Or there were basically then also query engines on top of that, or Hive, for instance. I think Hive translated into basically MapReduce jobs that we're running, right? But then fetching the data again. Spark has something SQL, right? Something similar, right? So as a kind of maybe successor of Hadoop in a specific context, right? They also had a query language in order to be able to do more dynamic querying on the data and so on.
Yeah, there was things like the Apache Hawk and Impala that would just bypass the whole MapReduce process and just use the HDFS file system.
Anyway, something like that, right? Anyway, so the thing is, SQL is useful, right? It's not completely useless, and it sometimes makes sense to express stuff as SQL, and even NoSQL database systems, as mentioned before, have SQL-like languages. Xentra has CQL, I think, which looks like SQL without joins, or Couchbase as a document database system has Nickel, which is like SQL for JSON, which has joins and is also allowing you some group bys and so on. Redis is having as a module Redis search, right, where you can basically define indexes. It supports automatic indexing. Good, the query language doesn't look exactly like SQL, but it looks also like an expressive query language, a little bit more like Lucene, let's say, right? So meaning a lot of NoSQL database systems actually have some query languages in addition as well, right, for being able to do some analytical stuff. But Martin is right that let's say the more traditional BI stuff is using SQL in a sense, right, to access it. There are some abstraction layers. You could, for instance, use Presto as a project by Facebook, right, which is a kind of distributed query engine which you can put on any kind of data store in order to bridge this gap of SQL for analytical purposes, for instance, right, by referring to whatever data store you have a connector for, right, and query the data out of it, or the SQL way, just as an example, right. And there is indeed another aspect that this traditional approach, let's say, again, it's a coexistence, is also kind of there are other approaches as well. Hadoop was one which I mentioned before, but there's also now this whole field of, let's say, artificial intelligence, machine learning, right, where it is about processing data in real time, building models, right, and you can say this is also analytics, right, and the tool set is completely different than the traditional BI tool set, right. So you're using something like Jupyter notebooks in order to get insights to your data instead of doing some reports in whatever Tableau or whatever you used with SQL in the past, right? So it's not. I'd say the statement is in general true, but not entirely true, because there are a lot of facets regarding it. Does that make sense?
Now that our opponents have completely switched sides, apparently. Maybe
it's just a fair
and balanced view from both of us.
It's just a fair statement, and by the way, I would not say that the one is possible without the other, right? So it's kind of common nowadays to not just say, hey, I have my analytical system there and I have my real-time database system there. It's actually often a combination of everything, right? So meaning what you have is you do your speed processing or real-time processing, and you do your analytical processing, and applications often basically incorporate both aspects, let's say, right? So they combine the analytical aspects with the real-time data, or they basically even do predictive analytics, or based on models that were derived from let's say deeper analytics or current real-time data flying in, right? So it's not like there's this analytics world and there's the operational world. Actually, modern systems are leveraging everything to a specific degree, right?
Yeah, as we are rapidly approaching our 4-hour mark with regards to the next podcast, maybe it's now time. Sorry, I'm of course only joking. Maybe now's the time for some final thoughts on the subject.
Really? Are we already done? Maybe I talk too much.
No, not at all, David. Not at all. No, we should keep the duration of the podcast to, I think, 4 hours. Given the fact that we're now stretching to 5.
We could touch a little bit on future, right?
The future, exactly. IBM mainframes are here to stay. So is IMS. DB2 alongside, NoSQL databases have their place. And thank you for listening. Joke, go ahead. Martin, go ahead.
Shall I go first? All right. So, anybody following the database world will see that there are constantly people innovating, mainly, both in the analytical side and the planet scale side, as you call it, Chris. But there are innovations in, let's say, the way they are architected. Happening. There are innovations happening in the way they use hardware or scalability, and I think so in short, it's a constantly evolving scenario. But as you can see, the relational database here to stay, NoSQL databases are here to stay. The graph databases, yes, they have a very good piece of functionality and use, but then I wouldn't call them mainstream as such. Or maybe doing them some injustice.
Martin, sure if it's any consolation, Richard has just deposited an undisclosed amount of bitcoins in our account, so you're free. You're free to plug your employer if you want to.
Yeah, so we are in the analytical space, so that's clearly our domain, and we use GPUs to accelerate database workload. So that's clearly a hardware play. That's good. It's making use of hardware innovations, right? So if, as you mentioned, quantum technology comes along, I'm sure someone will come up with a quantum technology database after that.
D-Wave, if you're listening, yes, the address is sponsor at linuxinlaws.eu, and we do take bitcoins. Yes. David, go ahead.
I'm not sure. Maybe I should mention that the grumpy old coders are taking bitcoins as well, right?
Okay.
But I need to invent an email address now, right? So, anyway. I mean, GPU stuff and so on is actually, I think, a good point, or sounds like something which is really useful in the future. I personally think that there is a convergence happening in the market. What I have seen over the last years is that let's say relational database vendors desperately try to add additional functionality to kind of keep up with the NoSQL vendors, because they are disrupted by the NoSQL vendors. But it's not exactly the same, right? As mentioned before, you don't just turn a relational database system into a graph database system because you offer a graph API. The same way you don't turn it into a document database system by just allowing to do some SQL which involves some JSON path queries, right? That's not how it works, right? Because at the end it's all about efficient access for specific purposes and so on. And I think the convergence is not happening just from the side of the relational let's say, side, but also from the NoSQL side, let's say, right? NoSQL vendors are adding additional functionality as well, right? For instance, new consistency models are addressing something like asset transaction compliance better than before, right? But the difference is that the approach of a relational database system is more, I'm coming from a system which is promising you to be general purpose by kind of having all this overhead and this huge package I'm carrying with me, whereby on the other hand side, the idea was I'm coming basically with a much lighter package, and I'm now basically allowing others in a controlled way to add additional functionality, right? And this additional functionality is then optional and not mandatory in a lot of cases. A good example, for instance, is Redis. In Redis, there are modules, right? There's a module which is adding querying, indexing, full text search. There's a module which is adding a graph engine and also Cypher as a graph query language. There is a module which is adding time series functionality, right? And you're not enforced to actually use it in any way or even to carry it around, right? You can decide to deploy this module or not to deploy this module by gaining specific functionality or not gaining specific functionality. And at some point, there will also be and I think Redis Raft was already announced during RedisConf, right? There will also be the possibility to do our CP system like stuff and maybe at some point even our different kinds of transaction management and so on, right? So meaning there is a kind of run happening between the NoSQL systems that are kind of becoming more and more flexible by aiming to fulfill more and more purposes without being general purpose systems, whereby you have on the other hand side this relational database system, which is kind of saying, hey, I'm a general purpose system, right? And I'm just promising whatever you need by actually carrying a lot of heavy weight around for no reason, right?
Yes and no. Some databases have that carrying around principle, but databases like Postgres have a similar modular approach. So, pluggable column stores and pluggable geospatial extensions.
Yeah, I get it. But the API, right? So the difference is that with the Redis module, you get basically a different API for dealing with time series or doing search or whatever, right? The module comes with a data structure and let's say an API which gives you efficient access to this data structure, whereby in a relational database system, and I would say this is the case in Postgres, I didn't double check this. I would say whatever you plug in is on a level which involves anyway some of going through the stack, right? So it will have more overhead than just basically going to the low-level API, which is exposed by Redis.
Modules, that's right? Correct. They are plugins. That is not complete new pieces of code, as you say. So from that point of view. But you're right, they're both converging in both directions. I would agree.
And my bet is that our NoSQL will long-term win this, right? But that's just my bet, and it's really just a guess. But my opinion, and maybe we can close it with this. My bet is NoSQL will win this convergence battle, and I guess your bet is that SQL will still be around in 50 years or whatever.
Definitely.
I mean, probably the best
It also comes down to the type of use cases. I mean, not everybody needs a plan scale database, so therefore a multi-purpose database is far more suited, so they don't have to learn 10 different technologies, for example.
I mean, on this conversion thing, the last statement is actually something called ToroDB, right? That takes the MongoWire protocol and maps it onto the Postgres engine, which is probably the best example for your proven point. The details, of course, will be in the show notes. ToraDB, if you're listening, if you're looking still for a sponsoring slot, contact us at sponsor at
Shameless, just shameless, man. Yeah. So,
David, this is the way you do it.
Don't forget to listen to Grumpy Old Coders.
Yes.
The podcast, right?
David, our email address is sponsor at
That's a good idea. Maybe the Grumpies could sponsor.
Man.
And of course, that has been more than a wonderful 2 hours, maybe 3. Any closing remarks for the next 60 minutes before we close this podcast off?
Yeah, I'm shutting up now, right? Because otherwise it never ends.
Just go ahead.
No. There's nothing to say anymore. I just want to say thank you for inviting me, right? And listen to Grumpy Old Coders.
Thank you very much.
Thank you, David.
Thank you for your time, David. Much appreciated, as usual. And look forward to having you both back at some stage. Martin, any final remarks from the dark side in terms of the old dinosaur world of SQL?
Well, I don't know. I
Before
mean,
we close this off.
If you're talking about old dinosaurs, you keep mentioning the mainframes. It should probably not mention dinosaurs. Yeah, no, it was good discussion, and I think David and I agree on many things on this anyway. To me,
well, I mean, people don't get confused. I mean, if you just take a look at the commit history of something called Postgres, which is probably one of the most popular SQL databases, it's still up and running in terms of it is still alive.
Yeah, indeed. Still, right? Still. No, I'm not going to buy it. Yeah,
it can still be more popular than Redis. Yeah.
And I want to apologize to all my friends at Ingress, by the way, right?
You have friends at Ingress?
Yeah, indeed. I still have, right? I worked there for a bunch of years. Okay. Yeah, but maybe one last thing, right? So actually, there's a new, and I'm not kidding. I mean, it's self-promotion, but anyway, I'm doing it. You can cut it out if you want. But there is a new episode of Grumpy Old Coders coming up, and the only reason why I'm mentioning this is because Christoph reminded me when he said the dark side, because the episode title is this time the dark side, and this is about let's say and maybe this scares people away, but the topic is this time a little bit less technical. The topic is actually a serious one. The topic is more about, let's say mental health issues or struggles and challenges, or in the context of the dark side, right? In the IT and software development business, all right? So,
okay,
not a funny topic anyway, or I had the feeling maybe this is something which can be discussed in a podcast together with Thomas. So, if you want to hear our opinions, Thomas or so the other Grumpy Old Coders and mine, right? Then stay tuned. We will publish it soon. Right?
Absolutely.
Thank you.
David, thank you very much for participating.
Thanks,
and it has been a pleasure as usual. And as I said, we'll get in touch one way or the other, and I'm really looking forward to having you on the show together with Thomas at some stage.
Yeah, sure. You're welcome. Thank you for having me. Bye.
Bye. This is the Linux Inlaws.
You come for the knowledge,
but stay for the madness.
Thank you for listening.
This podcast is licensed under the latest version of the Creative Commons license, Tab Attribution Share Alike. Credits for the intro music go to Blue Sea Roosters for the song Salute Margot, to Twin Flames for their piece called The Flow, used for the segment intros, and finally to Celestial Ground for their song Sweet Justice, used by the Dark Side. You find these and other ditties licensed under Creative Commons at Jamendo, a website dedicated to liberate the music industry from choking copyright legislation and other crap concepts. Any questions before we start the podcast?
Yeah, what is it about? Just database systems, I guess, or is
You
there...
have been volunteered, David, to represent the NoSQL side of the house. Whereas Martin, given his age, is actually presenting the SQL part, and I'm just doing the moderation. That's all.
Okay, fine.
We
should be an
can
easy
work.
one.
And no,
Yes,
it's not a battle. Very important, but just a discussion.
Fight.
Yes. You see, David, this is something that we do want to avoid. If that makes sense.
We know what we're
Oh,
talking
Martin!
about.
Oh, I forgot. There's a ground rule. You cannot mention Postgres.
In that case, we can't mention Redis or Couchbase.
Or Redis or Couchbase
Yeah.
or whatever, right?
It's okay, guys. Anything goes. This is. I mean, the show is not as explicit, so you can swear if you want to. Martin, if this whole RT thing doesn't work out, just take a couple of Udemy courses and you're fine as a politician. Rest assured.
I don't need a course for that.
I'm talking about the fine-tuning now. I'm not talking about the basics.
Okay.
You've been listening to Hacker Public Radio at hackerpublicradio.org. Today's show was contributed by an HPR listener like yourself. If you ever thought of recording a podcast, then click on our contribute link to find out how easy it really is. Hosting for HPR is kindly provided by anhonesthost.com, the Internet Archive, and rsync.net. Unless otherwise stated, today's show is released under a Creative Commons Attribution Share Alike 3.0 license.